Hi, in this video we are going to talk about the relationship between concentration and conversion in reaction engineering. Now, these are two terms which you will come across a lot when you talk about reactor design. So, we know that we have batch, semi batch, or flow reactors. And let's say, let me write a reaction. So, let me write the reaction as AA plus BB plus, considering presence of inerts, II gives product RR plus II. So these small letters are the stoichiometric quantities in which the reactants and products are present. I, of course, the inert does not react, so it just passes through the reactor without any changes. Now, to have a measure on the extent of reaction, we have two important terms. One is the concentration term, and the other one is the conversion term. Generally, we denote concentration with capital C, subscripted by the notation for your particular reactant species or product species, and the same goes for conversion term, except that we denote it as X with the subscript. Okay, so let me just write Cj or Xj depending on whatever your J is, be it the reactant or the product. So this relation between these two quantities, concentration and conversion, they depend on a lot of factors, and based on the factors on which they depend, there are three special cases that we find in our reaction engineering literature. So let's talk about the first special case, that is constant density batch and flow systems. So constant density batch and flow systems means that the density remains constant throughout, and you can understand that this is absolutely applicable for liquid reactions case. Okay, so you have a constant density batch or flow systems where liquid reactions occur. Also, some gas reactions which are run at constant temperature T and density. So I am denoting density as rho. So if now I want to relate this concentration and conversion, let me work with this concentration of A and conversion of A. Then we can write it as follows: Xa equals to 1 minus Ca by Ca naught. Ca naught means the initial concentration of A at the starting point of reaction, and dxa equals to minus dca by ca0. Also, you can write dca equals to minus ca0 dx just by cross multiplication. And by constant density, what I mean is that epsilon a equals to Vxa equals to 1 minus Vxa equals to 0 by Vxa equals to 0 is equivalent to 0. That is the volume ratio between 100% conversion and 0 conversion. That is remaining 0. So now you know that this is a constant density system. Okay. Also, if you want to relate interrelate between the different constituents or the different participating species in the reaction, then you want to relate the changes in B with respect to A, or changes in R with respect to A. In that case, what you will do, you will use Ca0 minus Ca by A, the stoichiometric quantity in which they are present, equals to Cb0 minus Cb by B equals to Cr minus Cr0 by R. Or another way to write this is Ca0 Xa by A equals to Cb0 Xb by B. Okay, these are the important relationships in case of a constant density batch or a constant density flow system. Now let us consider another special case. So next special case 2 is batch and flow systems of gases. I am writing it in capitals, gases of changing density but with constant temperature and total pressure. T is for temperature, pi is for total pressure. So here the density changes because of the change in number of moles during the reaction. Okay, but the temperature and the total pressure remains constant. So another requirement of this kind of reaction is that the volume of the fluid element changes linearly with conversion, that is V equals to V naught multiplied by 1 plus epsilon A Xa. Now epsilon A, you know, that is the volume ratio, Xa is the conversion, V naught was the initial volume and V is the final volume. So there is a linear relationship between the initial and the final volume within the reactor. Now, if you want to relate the concentration terms and the conversion terms in this case, then you will have expressions like Xa equals to Ca0 minus Ca by Ca0 plus epsilon Aca, and accordingly as per the differential logic you can write dxa equals to minus Ca0 multiplied by 1 plus epsilon A into dCa divided by Ca0 plus epsilon A Ca whole square. Another way to put this is like Ca by Ca naught, just mathematical manipulations and you will get this. Ca by Ca naught equals to 1 minus Xa by 1 plus epsilon A Xa, and accordingly you can also get dCa by Ca0 equals to minus 1 plus epsilon A by 1 plus epsilon A Xa whole square whole multiplied by dxa. And this, you remember, this is for epsilon A or volume ratio not equals to 0. So here a variable volume concept is associated. I'm not going to do the derivations of this because these are obtained by manipulations given, I mean mathematical manipulations of one of the equations. You all you need to do for exams is you remember one of the equations and then you can do the mathematical manipulation and obtain the other terms. Okay, so you can use this. Now if you want to relate the other components, let's say B with respect to A, then what will you do? So in that case, for relation between reactants, we have epsilon A Xa equals to epsilon B Xb, and A epsilon A by Ca0 equals to B epsilon B by Cb0. When you want to relate products and inerts, for products, product is R and inerts, that is denoted by I in that general equation we discussed. So in that case, Cr by Ca naught equals to R by A Xa plus Cb0 by Ca0 divided by 1 plus epsilon A Xa. Another one to relate the inert is Ci by Ci naught equals to 1 by 1 plus epsilon A Xa. So these are the relations that we use for batch and flow systems of gases of changing density but with constant temperature and total pressure. Now we'll go to the third case, the last case, special case number 3, where we study batch and flow systems of gases in general. That means we have varying temperature, total pressure, as well as density. Okay, so the previous case was density was changing, but temperature and total pressure were constant. But in this special case 3, we have all three main parameters, that is temperature, total pressure and density varying. So what will happen in this case? Now here I am going to write the chemical equation according to which the reaction will progress. So it will progress like this: AA plus BB gives RR, and A plus B not equals to R. Okay. So in this case, the first thing you will do is you will pick a key reactant. Okay, you need a key reactant which becomes the basis to determine the conversion. So let me say that I should write choose key reactant. So I am choosing A as our key reactant. Okay, then ideal gas behavior considering ideal gas behavior, we can write Xa equals to 1 minus Ca by Ca naught multiplied by T pi naught, that is the initial total pressure, by T naught pi divided by 1 plus epsilon A Ca by Ca naught multiplied by T pi naught by T naught pi. Okay, then again you can just interchange the sides and obtain the expression for Ca by Ca naught. So I am leaving this to you, what will be the expression for Ca by Ca naught. All you need to do is interchange the sides for the expression that I have just written down. Now in terms of Cb, how will you relate? So Xa equals to Cb naught by Ca naught minus Cb by Ca naught multiplied by T pi naught by T0 pi divided by B by A plus epsilon A Cb by Ca naught multiplied by T pi naught by T0 pi. So here again you can do mathematical manipulation and you can comment on this video what will be the expression for Cb by Ca naught. So just you need to cross multiply and make Cb by Ca naught as the subject of your equation. Now relating the product, Cr by Ca naught equals to Cr naught by Ca naught plus R by Axa divided by 1 plus epsilon Axa whole multiplied by T0 pi by T pi naught. Okay, so this becomes your expressions. Now we can consider this ideal gas behavior when we have low pressure considerations, but for high pressure considerations, so let me write, for high pressure we are dealing with non ideal gas behavior. In that case we have to bring the compressibility factor into play. So Z is the expression for compressibility factor. So now in the equations we will simply replace T0 pi by T pi naught by Z0 T0 pi by ZT pi. Okay. So okay, I missed one thing. This will also be T0 pi 0. So you will be replacing, right? Now this Z becomes the compressibility factor. Okay. Now in this case if we choose B as our key reactant, then we can simply relate as A epsilon A by Ca naught equals to B epsilon B by Cb naught, and Ca0 Xa by A equals to Cb0 Xb by B. So if you have liquids or isothermal gases, another like a consideration for this same case, for liquids or non sorry my bad, for liquids or isothermal gases with no change in pressure and density, then we have to consider epsilon A tends to 0 and T0 pi by T pi naught tends to 1. Okay, and accordingly you have to obtain the relations. Now this serves as the basis for our uh, you know to progress with reactor design. Now mainly the first two special cases are very important. Okay, so special case 1, constant density batch and flow systems, and special case 2, batch and flow systems of gases of changing density but with constant T and pi being the total pressure. So these two special cases are very important. The third special case is like a very general study of gaseous systems, and it is more prevalent to study this kind of systems when you are dealing with industrial scale reactors, or for research to find alternative reactor designs for gaseous systems. Therefore with this we come to the end of the overall introduction to reactor design. From next lecture onwards we will talk about ideal reactors for a single reaction. That is it. Thank you.